Welcome back, students. So to start with the derivation of depth of neutral axis, this is the same diagram which we have discussed earlier in the previous video. So this is basically a doubly reinforced beam section with AST and ASC here. Always you have to remember that ASC will be a lesser value than AST. That is the reason here I have shown randomly 4 bars and I have shown 3 here. So either it can be equal or ASC will be less than AST, because usually the compressive steel is lesser than the tensile steel. You cannot have AST value higher than ASC. So either it will be 4 and 4 or it will be 4 and 3, 4 and 2 and so on. Minimum it will be 2 bars in both the columns. So it is ASC, AST. This is the DC that is shown. C dash, this is C and T by M. This is the normal stress diagram of the singly reinforced section. This is the extra thing that we have marked here, that is C dash. And this is the depth that is at N by 3. C1 is acting. This is the same from singly reinforced section. This is an extra thing, that is C2. Okay, the force C2 that is acting due to the compressive steel in compression zone. So to start with, first we will consider from stress diagram. From stress diagram, using similar triangle property, we can write small c divided by n. So this triangle, small c divided by n, I can write it equal to c dash upon, so c dash upon this distance, which is n minus dc. So n minus dc. Okay, so I'm just taking two triangles, that is this bigger one and the smaller one. So this is the compressive stress in concrete, this is the compressive stress in compressive steel. Okay, so C upon N is equal to C dash upon N minus dc. Now here we can write, we know that N is equal to K times D, and we also know that dc is equal to E times D. We have taken this. Okay, so I can write this as C upon C dash is equal to K times D upon K times D minus ED. I've just substituted the value of N here and DC here. So then C dash can be written as, if I take this D common out and it will cancel out, then I'll have K minus E upon K multiplied by C. So I've just cross multiplied, taken this C dash this side, D and D gets cancelled. You can just simplify this equation and get the value of C dash here. Now stress in steel, it is TC, this particular value, TC is equal to MC into C dash. So if C dash is TC upon MC, TC is equal to C dash into MC. This is what I have written. Okay, this again is equal to MC into, we will substitute the value of C dash, that is K minus E upon K into C. I've just substituted the value of C dash in the equation. Also we know that MC is equal to 1.5 times M. This is according to the IS 456. That is, the modular ratio in the compression zone is 1.5 times the normal modular ratio. So therefore TC will be equal to 1.5 times M K minus E upon K into C. Okay. Now, if maximum stresses in concrete and steel are known, if we know the maximum stresses in steel and concrete that are developed, again from figure B, okay, again from figure B, that is the stress diagram, using the similar triangle property. We can write C divided by N equal to, considering the tensile stress now, T divided by M upon D minus KD. I will explain to you this in the diagram. Earlier we considered the triangles only in the compressive zone. Now we have considered the stress triangle in compression zone and stress triangle in the tensile zone. So this C divided by N is equal to T by M divided by this distance, that is D minus KD, D minus N. So if you substitute N is equal to KD, it will be D minus KD here. Okay. So from stress diagram we get this. So from here we will be able to get the value of K. Okay. So again I will write C divided by T by M equal to, this N will go here, N I will substitute it as KD, D minus KD. Again if you take the D common, we get K upon 1 minus K. Or if you just simplify this, okay, you get K is equal to MC upon MC plus T, where C is sigma CBC and T is sigma ST. Therefore, K value for a doubly reinforced section and for a singly reinforced section is the same. We derived the equation for K in singly reinforced section, we got the same formula. Here when we derived the formula for K, we again got the same formula, that is MC upon MC plus T, or M sigma CBC upon M sigma CBC plus sigma ST. What does this mean? This means that the presence of steel in compression zone does not affect the depth of neutral axis. Again, depth of neutral axis will remain same, that is N is equal to K times D, where K will be equal to this particular equation and D will be according to the section that is given to you. So whether there is steel in compression zone or there is no steel in compression zone, the depth of neutral axis will not change. It is going to remain the same. There won't be any effect of the compression zone steel on the depth of neutral axis. Now, by neglecting the concrete in tensile zone, obviously when we consider the singly reinforced section, we had neglected the tensile stresses in concrete. So similarly here we will neglect the concrete in tensile zone and equate the moment of compression area about neutral axis to the moment of tensile area about neutral axis. This is the same thing that we had done for singly reinforced section also. So by equating moment of compression area equal to moment of tensile area. We had done the same procedure for singly reinforced section also, so we are doing the same thing here. Equate both. Okay, here now what is the area in compression? It is this particular rectangle, so it is B into N, area of the rectangle, and the CG of this area from neutral axis will be at N by 2. Okay, so I will write it equal to B into N, that is area of rectangle, and it is at N by 2 from the neutral axis. Plus, I will have to add now. I will have to add the area of steel in compression that is provided here, because we also have ASC here. Earlier there was no ASC, so in compression zone it was only the area of concrete. Now it is area of concrete plus the area of steel that is there in the compression zone. So we will add this, and at the same time we will have to remove the same amount of concrete, because we have considered concrete as b into n, that is the entire rectangle. So when we put steel, we have to remove that much amount of concrete. So we will add the area of steel and minus the area of concrete in this particular section. This is again the concept of equivalent area. Okay, so here this will be equal to, first is total area of total rectangle, then we will add the area of steel. Now when adding the area of steel, we have to consider the modular ratio, that is MC into ASC, as it is the area of steel in compression, and it will act as N minus DC from neutral axis. Now how this N minus DC is, again going back to the diagram. Okay, it is from here, from neutral axis to the center of the reinforcement. So it is basically total N minus this distance DC will be from the center of the reinforcement till the neutral axis. Okay, so this is the distance of CG from neutral axis. So we write it as MC into ASC into N minus DC. Now this is the total area. So from here we will have to minus same area, that is ASC, area of concrete that is provided. Because we put steel, similar amount of concrete has to be removed. Okay. Now this will be equal to moment of tensile area. What is the moment of tensile area? It is the same M times AST, that is area of steel, and the dimension is D minus N, or the distance is D minus N. Again from the neutral axis till the center of the reinforcement. So now we can rewrite this equation as Bn square by 2 plus MC ASC into N minus MC, just open all the brackets and try to simplify this equation, ASC into DC minus ASC into N plus ASC DC. I've just opened all the brackets here and simplified the equation. So if you rearrange this, we get Bn square by 2 plus MC minus 1 into ASC N minus DC equal to M times AST into D minus N. Now here we can substitute the value of MC as 1.5 times M. So further the final equation will be Bn square by 2 plus 1.5 times M minus 1 ASC N minus DC equal to M times AST into D minus N. So this is the final equation for depth of neutral axis for a doubly reinforced section. Now in this equation all the terms are known except N. Okay, N is unknown. So hence depth of neutral axis can be located. Now in the above equation we can also substitute N is equal to KD and DC is equal to ED. We can substitute this or we can keep the same. So basically we can find out the value of N here and then get the value of N by multiplying K into D. Okay, so we have to remember this equation to solve the numericals of doubly reinforced section. Thank you.